Hi guys, welcome to week 8. This week's experiment is actually pretty cool. We're going to be experimenting with water and doing what we call like supercooling. So supercooling is actually the process of lowering the temperature of a liquid or gas below its freezing point without it becoming a solid. This happens because it freezes so rapidly that the molecules literally have no time to form a structure of a solid. So a supercooled liquid is definitely considered unstable. So simply by adding a little bit of rust or shaking a supercooled water bottle, which is what I'm going to show you in a minute, or by using unpurified water, even just like the minerals, will cause it to, hold on a second, sorry about that, will cause the water to solidify quickly. So okay. So what I've done is, I want you to see my experiment while I talk. So water is usually liquid when it's room temperature. And when this is the case, the water molecules are all moving around and it allows the liquid to flow. When we freeze a liquid, it becomes solid, which means the molecules lock into place. They still vibrate, but they're not moving around and past each other, so the liquid can no longer flow. When water is frozen to below 0 degrees, where it should become ice, it's still hard for the water to make the transition without somewhere for the ice crystals to start growing. We call this a nucleation event. So this is what I'm going to attempt to show you today. Now, if the water is not pure, then impurities in the water will cause it to freeze faster. So for our experiment, I used some Zephyrillus, which is natural spring water, and it's kind of, I'm not sure how purified it is, so judging by the first bottle I took out of the freezer, it's already starting to freeze, so I'm pretty sure it might work. So basically what I've done is I've put some water bottles in the freezer, left them in for 2.5 hours, long enough for the liquid to freeze without creating a state of solidity. And I've carefully taken the first couple bottles out of the freezer, and I'm gonna try to create a shock wave, which is the nucleation event, and it will create a crystal-like nucleus which the water molecules can latch onto, and like I said, form a lattice where the molecules can line up in a structure forming a nucleus for the other crystals to grow off of. So what I'm going to do is kickstart this by creating a shock wave, which almost happened but didn't. You can see this water is liquid because you can see the water moving around at the top. So I just took this out of the freezer, and I'm going to, whoop, and there it goes. You can see just by shaking it around, it's already forming some ice crystals inside. Let me shake it a little more. You can hear it in there that it's slushy. Let me take one out of the freezer right now, fresh out of the freezer, and do it. Okay, here's another one. There it goes. So you can see the ice. It just, as I shook it, there's still water in there, but it also formed kind of like a slush inside the water. So water usually freezes at 32 degrees, but it actually can be super cooled at a standard pressure down to its, it's called its crystal homogeneous nucleation. That's almost -55 degrees Fahrenheit. So as I mentioned before, the water is supposed to be pure, and that could also be done. I suppose I could probably use distilled water because other processes like reverse osmosis or demineralization can do that. So I'm gonna, since I've already shown you by creating the jarring motion, causing the shock wave to go through, next I'm gonna take some ice cubes right here from my refrigerator, and we're gonna try another experiment by, I'm gonna try to pour some of this cold water from the freezer, onto the ice cubes and see what happens. Oh, check it out. It's growing. See that? So pouring the cold water onto the ice cubes, the solid molecules of the water in the ice cubes, the water, which is super cooled, latches on and it branches out and forms like a ice crystal, which is basically growing now from top to the bottom. Isn't that cool? So, sorry, I'll hold it up. But that's pretty cool. So I imagine that's how they make fake snow machines. I'm going to try one more experiment here. You bear with me. This time, I'm going to take some of the water. I don't know why I chilled the glass, but I'm going to pour it into this glass. And actually, just by pouring it into the chilled glass, might be a little hard to see, but this actually formed ice crystals and slush itself. I guess that's how they make the nice chilled Cosmos when you go to a restaurant. In addition, I'm going to take an ice cube. I'll use an unchilled glass. So another way, let me just pour. I'm going to pour some of this icy water. It's still in its liquid state, but it should still be cold enough that I'm going to take an ice cube. Try to get this up here so you can see. Stick the ice cube in the water. Okay, so I think that this water might actually have warmed up too much. So let me open another bottle that hasn't been opened yet. Let's try pouring the ice into this glass and then see if this ice or water is still cool enough. I'm going to dip, oops, whoa, okay, I dropped the ice cube in there, but as you could see, by dropping the ice cube in there, I immediately have a cup full of slush, which is, I can make a snowball out of. I guess what we've done is we've made a nucleus with the super cooled water and the crystal structures from the ice cubes, and just made snow. So the water latched onto the ice cube, and we have all of these examples of this super cooling process. And this was one of my favorite experiments. I hope you enjoyed watching.